Hi friends, this is a short video on finite element analysis FEA using SolidWorks. The first part is on the basics of finite element analysis, and we will see how the basic concepts of FEA which are usable for SolidWorks. Before we go into the concepts of finite element analysis, I have a question. How did you calculate the area of this kind of basic shapes during your school days? Say if it's a square having some dimension, we have equations. We used equation, right? And if it is a circle, we have again equation to compute the area. If it's a triangle, based on the kind of triangle, we have equations. But if we had not had the equations, even in that case, we had a method of identifying, computing the area of this kind of shapes. Do you remember that? We had used graph sheets. Do you remember? So how it was done? We have used graph sheet. On the graph sheet, we will make the square or the shape for which we have to identify the area, and we will count the number of squares present inside the area to compute the area, right? Because we know that each square of that graph is 1 centimeter by 1 centimeter, that is 1 square centimeter. That means 1 square is 1 square centimeter, and we will count the number of squares, and finally we will add all the number of squares. Then we will identify what is the total area of the rectangle. The same method we had applied with circle also, but when we identified circle, we can see that as in the case of rectangle, the line of the graph lines, in the case of the circle, it was not aligned. Still, we have done some kind of corrections and we could reach the area approximately, and we have also seen that the area obtained by this method, that is by adding the number of squares, we can improve the accuracy or the result of this computation if the area of each cell, that is 1 square centimeter, if it is still reduced. That means for this kind of shapes where the area, the small elements are not aligned with the given profile, then we will do some kind of corrections, and the error in the computation can be reduced if the small area taken for computation was still smaller. That we have experienced in school days. Now, if we had to identify area of such kind of shapes, kind of a quadrilateral, we don't have a ready equation to compute it, there also we could apply the same method of identifying the number of squares inside this profile, and then we'll add it. Okay, and even if it is a complex or undefined shape like this, there also we could apply that. What was the advantage of this or the features of this method? This method arrived at the result by adding same parameter. Here the parameter we have taken was 1 square centimeter, and we counted the number of square centimeters available inside the profile and we added it. Then we arrived at it. Is the result was exact? No. It was approximate result. But is it erroneous result? No. It has got reasonable accuracy, and we had method to improve the accuracy of the area also, right? This was one of a kind of a finite element method we have adopted in our school days, where the small area that we have used is called as a finite element, and we have added the property of the element. The property is the area of the finite element. We have added all this and we identify that property, that is the area of the bigger profile, square, circle or quadrilateral or whatever. So that's how the finite element method works. The same method we can apply in our engineering applications as well. For example, say you have a cantilever beam, say like this, that you see here. There's a cantilever beam like this, okay, and it has got one side is fixed and the other side is cantilever, and imagine that there is a force applied out here, and we know that we have equations to compute what is a deflection, what is a strain, those kind of things in this. And if there is another cantilever beam like this and the force is applied in only one direction like this, in this direction, say, we know what is the stress and we have the equation to compute it. For this kind of simple elements, we have ready equations. But imagine that there is a section like this, or even a complex section having a variation of this kind of variation of cantilever beam. Then can you go for that equation? No. There we apply the same finite element method. What we will do? We will discretize the whole domain into equal spaces having similar properties, and then we will identify what is a total property of the object by computing that property of each element. So in the previous case of computing area, we have taken one element as the area square, 1 square centimeter, and the property was area. And finally, we added all the areas of the small areas, and then we identified the area of the object. The same method applied here. If you want to apply deflection of this beam, we chop it into multiple elements, then we will find deflection on each element, then what we will compute what is the total deflection or the maximum deflection that happens and where it happens, those kind of things. Apart from that, we can identify what is the deflection happening in any region by applying the equation. This is our approach in finite element analysis. So let us formally see what is finite element analysis. Finite element analysis is a process of predicting an object's behavior based on calculations made with the finite element method. This finite element method, actually it is a mathematical technique, whereas finite element analysis, it is an interpretation of the results that we obtain from finite element method. So FEA gives engineers insight into complex problems which will help them make more informed design decisions and in real world situations. FEM uses math to break complex system into smaller, simpler pieces, and we call the simpler pieces as elements. Then we apply differential equation to each element individually and solve it using the power of the computer. So FEA is the application of finite element equation modeling method equations and is the basis of many types of simulation software. In SolidWorks also, we have all this approach. ANSYS is one of the finite element analysis software. Abacus is another example. NISA was there. It is used to validate, test, design safely, quickly, and economically, because when we analyze the complex situations, say even if it is a beam for a building, even before making the beam, we can analyze what should be the cross section of the beam and how much load it can withstand, or in order to withstand this much of load, how much should be the cross section and how the material should be selected, those kind of things, even without building it. That means we can safely, without destroying anything, we can do it, we can quickly analyze it, and it is economical as well. Now, what are the possibilities if you think for finite element analysis? The FEM makes it possible to simulate the physical world without the expense of time or risk of building the physical object or prototype. These models are used to solve various conditions and scenarios across a variety of industries, especially with complex engineering problems, high-risk environments such as aerospace, biomechanics. Say, if you want to develop a new aeroplane having a different kind of wing, you need not have to build the aeroplane and the wing itself as such. So you can model it, you can analyze it, and you can verify and confirm it. After that, you can go for prototype or in testing. If the finite element method is done perfectly, even without testing, we can straight away go for building of an aircraft. So that is the power of finite element analysis. We can design the chair, what you sit. If you want to see the magnetic field that is developed by a wireless device, how it will be, how much impact it has got, those kind of things. So if you want to model the blood pressure inside your vein, it is not needed to analyze with various human beings and all. We can straight away do the analysis in the virtual environment with the software like this. It has the ability to solve approximate high irregular dimension problems. Any physical behavior described using differential equations can be solved. And as I said, the solutions are approximate, but accuracy is reasonable. How FEA works? The finite element analysis works by discretizing the domain of our interest, then assembling the equations to solve the engineering problem that we have seen, the concept. That is, dividing the domain or discretizing the domain into components, and we call it as each component is called as an element, okay? And the element is, and the process is called as meshing. So altogether, how the finite element analysis process is, we can categorize the process wholly into 3 steps. One is a pre-process, second one is the process itself, the third one is post-process. The pre-process is to define the physics and the real world conditions to be used in the model. The process is dividing the object into finite elements and apply the relevant physics equations and then apply the conditions and solving it to get a result. Then post-processor is the computer will give the result. We have to analyze the result and interpret the implication of the result. When we go for finite element analysis, we need to be familiarized with 3 terms very clearly. One is discretization, another term is node, another term is boundary condition. What is discretization? It is a process of dividing a continuous structural system. We have taken an example of a structural system only now. This is applicable for all the examples that we take. So dividing a continuous structural system into smaller, manageable number of parts, it is called as an element, and to facilitate numerical analysis. That is, we can say that the structure is modeled using finite number of elements. Finite number of finite elements, right? That means finite means we have countable number. Finite, another meaning of finite is small element, right? And we use the same element to discretize the entire area. In the case of computation of area, we have used one particular element called as a square area, square unit, right? And we have used the same element across the domain. Like that, in finite element analysis also we discretize it using element, and the same element will be used. For example, imagine you have a mild steel beam like this, and it is supported like this. One side it is hinged, another side it is on a roller support, and there is some load here. Say you are going to discretize it to various pieces. Say now I have discretized it into 10 pieces. This division will help us to identify what is the parameter on each element, and based on that we can predict the behavior of the system. That means dividing the entire domain into finite element sections is called as meshing or discretization. So this what you see here is a meshed model. Here we see little more complex meshed models. Here say an analysis where airplane wing is discretized like this. This is a mesh you can see here. See here there is another model of heart. There also we see that the model is meshed. I have told you that finite elements are used to discretize the domain. This slide just shows summary of basic elements that are used in finite element analysis. There are elements like 2-noded elements, line element. It is a one-dimensional element. That means it has got 1 degree of freedom, displacement only in one direction. The element will have 2 nodes, one at each end of the line element. This kind of elements can be used for analyzing trusses, beams, roads, etc. There are 2-dimensional triangular element looking like a triangle. It has got 2 degrees of freedom, displacement in x and y directions. It will have 3 nodes. You can see that triangle will have 3 nodes. Okay, and it is used for plate bending, 2D stress analysis in the quadrilateral element. It is 2-dimensional, 2 degrees of freedom, again x and y. Quadrilateral means 4 nodes. Okay, like that there are many kinds of elements used in finite element analysis, and we choose the elements for discretizing the domain judiciously by understanding the requirement of the analysis. The meaning of the statement can be understood more clearly only when we apply this discretization for various applications. Let us see another term, node. Node is a point where elements are connected. See, I have told you that in the case of a cantilever beam, if it is divided to say 3 elements, 1, 2, 3, then the end points are called as nodes. So the nodes are the points where the degree of freedom are defined and solution is calculated. That means when even we apply the equation over the element, the degree of freedom, the moment are defined over the node, the boundary conditions are applied over the nodes, the computational results are also obtained on the nodes. So nodes are very important. See, even if you see the complex design like this, even if it is discretized like this using tetrahedron element, then the load is applied on nodes, and the movement or restrictions are also applied on nodes. So nodes are the points where we give the conditions, restrictions, and computed results, etc. Another term, a very important term, is a boundary condition. It is the constraints that we give on the system, such as fixed support, whether there's a roller support, whether we have applied forces, moment, etc. So these are used to solve the problems. In the case of structural problem that we do in our classes, we can say that there are two types of typical boundary conditions. One is a displacement boundary condition that will specify what is the displacement of node. Say in the case of this cantilever beam, what is the displacement at the fixed end and what is the displacement or degree of freedom available for the last node. There are force boundary conditions, that the force or a moment that is applied, that is defined or not. So that is a boundary condition. So overall, if you see how the FEA works, we have to model the required object and the environment. We have to provide the material properties and choose the physics to be applied. Then we have to do the meshing, discretization using the suitable finite element. After that, we apply the boundary conditions, restrictions and all, and then we place a request in the system to run the model so that it will develop the solution based on the required constitutive equation. Then it will give the result, and the result we have to analyze and we have to interpret whether the results can be usable or whether the system will work. For example, if I want to design a bench for my classroom where 3 students are to sit on the bench. So here I have to model a bench, we have to mesh the bench, we have to apply what are the conditions for that, like some supporting and what are the kind of loads are applied. So that's the boundary conditions we are giving. Those kind of things are to be fixed. Then we will go for solution. So when we apply this, it will give a result, like say bending or the strain that is happening on the system or the stress that is developed. But whether the result given is acceptable, whether the deflection is acceptable or not for the purpose. So these are the things that will be decided during interpretation. What are the advantages of FEA? We have seen advantages. One primary thing is it is possible to model any shape or geometry of any size and typically of any material. Size means even nanoscale to a long passenger jet plane can be modeled, and any types of physics can be analyzed in this, like heat transfer problems, fluid dynamics problems, structural mechanics problems, magnetism, multi-physics problem, like say case of a magnet or rheological fluid. Say magnetism will cause rheological change, the flow property of the liquid will be changed. So how the flow property will be affected because of magnetic field? It's a cross physics problem. Like that in the case of design of seal, in the case of bike and all, in the fork there is a seal, right? So the seal will have to flare when there is a force, and the force can from the fluid in the shock absorber. So the fluid force problem and the mechanical structural problem of the rubber have to be connected to explain the working of that. Those kind of things are all called multi-physics problems that will go for various domains. Those kind of things are all can be done by using finite element analysis. Analysis have got advantages that it can assess even complex geometries, it can simulate any range of physics, it will save time, money, resources and all. What are the challenges typically on FEA? The output that we get is only as good as the input that we give. That means the finite element model depends on the accuracy of the information that we give to build the model. For example, if I want to design a clamp to hold air conditioner on the wall of my lab, we have to use a mild steel clamp, and we identify that it is to be fixed at 2 screws over here, and we give the material conditions, fixing property, that kind of restrictions and all, and we conduct the evaluation by considering the weight of the air conditioner unit and all, and finally we will design the clamp. That means we will arrive at a thickness or the strain or the deflection of the clamp. But the question is, the material property that we give inside the the software, whether it's the same as that the material property that we get in the real object, whether the fixing condition and uniformity of the material, whether the real thing and theoretical thing are the same, or the conditions that we have given in analyzing the result are good enough. So those kind of information is very important. That is, as long as we give better and correct information as an input for this analysis, because altogether it's a mathematical equation solving method. So whatever we give, it is to be correct, then we get the result, and that result can be more accurate to the real value. Here, the assumptions that take, such as the geometry, the material properties, the type of analysis that we choose, these are all very important in this. And for that, the person will require engineering or domain knowledge. That is another challenge here. Like any other software, just because of a common skill, we cannot interpret a result, or we can get some results, but the results cannot be believable. So that's another challenge. So assumptions and domain knowledge are very important. So FEA results should be done typically with experts. So people have to discuss when they do serious analysis, engineering analysis using finite element analysis. Even if we get a result, see, for any kind of analysis, you will get a result like this, say blue to red range. Even if you analyze an airplane wing, there also you will get this kind of distribution of colors. That does not mean that the result is acceptable. That means whether the value that we get for this kind of gradation, whether the value is acceptable or not. As I said, in the case of the design of a bench, if the value that you get, the deflection that you hear, say if you are getting 5 millimeter deflection over here, whether it is acceptable or not, that is your decision. When I design a chair, obviously when we sit on a chair, there can be deflection, say even 5 centimeter deflection can be there. For a mild steel tube for the chair, when you analyze it, if 5 centimeter deflection, if is it fine or not, that is your interpretation. So interpretation of result requires domain knowledge, analytical skill, and it is a responsibility of the engineer. It's one of the major challenges, and that is why finite analysis are handled by experts typically. We will have to develop the domain knowledge to interpret the result that it is given by software like SolidWorks, ANSYS, Abacus and all. So that's all about a preliminary information about finite analysis concepts and all. And how do we use SolidWorks for finite analysis, that will be continued in another section. Thank you so much.